the aim of my talk is to obtain the counterpart of Danforth-Petty's theorem for homogeneous polynomials. But this is impossible without giving some background, so I'll start with it. Okay, first I'll give some standard notations which are well known. We use, as usual, omega sigma mu to define sigma finite measure space. We use the notation like they are written here L0 and a kind of to denote, as usual, to denote the space of all equivalence classes of measurable almost everywhere finite real valued functions. Also, we will need the notation, we will denote E and F the ideal function spaces. For example, they can be LP space, LQ space. Also, I will use the notation of omega. This is the Cartesian product of omega 2, omega 1. Mu will denote the product measure. The history of integral operators, I'll show the definition just to recall it. The history of integral operators is a very long story. There are many researchers starting, it started, I guess, in the frontier of 19th and 20th century. And there are many investigations. In 1922, Stefan Banach investigated the integral operators in his PhD thesis, if I'm correct. And then in 1930s, a new interest was blushed to this type of operators in the problem of kernel representation of linear operators. So here on the slide you already saw the standard definition of a kernel representation. We say that linear operator acting between ideal spaces is kernel, or in Russian literature we say integral, or it admits kernel representation or integral representation if and only if this is fulfilled. You can see it on the slide. One of the waves of investigation of integral representation of linear operators started when John von Neumann was justifying the quantum theory. And there in his model, he used the operators which act in L2 spaces. And his question was, which operators on L2 spaces are induced by kernels? Of course, we mathematicians, we understand that in the place where someone is talking about L2 spaces, we can speak about LP spaces and about ideal function spaces. So the more general formulation of this question is the following: which linear operator acting between two ideal function spaces admits kernel representation? And various answers providing sufficient conditions for this question were obtained, but none of them was sufficient and necessary. And finally, in 1974, Professor Buchwalov obtained the necessary and sufficient condition for a linear operator to be kernel. You can see it here on the slide. He obtained this result for every linear operator acting between ideal function spaces, and it is kernel, it admits kernel representation if and only if it carries any bounded positive convergent to zero in measure sequence, carries into convergent to zero almost everywhere sequence. In other words, linear operator T admits a kernel representation if and only if it improves the quality of convergence. So, And another wave of investigation of integral representation is related to the following question: in which spaces do all bounded linear operators admit kernel representation? Here several results were obtained. It is exactly 1930s, but here I presented the result which was obtained by Kantarovich and Vulich in 1937, where he investigated. You can hear me, yeah, without microphone. Where he investigated linear operators which has as a range space the space of all bounded measurable functions. For example, Danforth obtained the same representation, but he was working with linear operators with values in, for example, LP spaces. Here a natural, this this equality provides us the correspondence, which is isometric isomorphism between the space of linear functions acting from L1 spaces to L infinity spaces to here. Kernels are taken from here. By the way, I have forgotten to say that this guy is said to be a kernel. So further on, while developing this theory, the question arose: what if we take not the concrete Banach space here, but let it be arbitrary Banach space, let it be arbitrary X, okay? This is the literature. Okay, and let it be the arbitrary, as I said, X space, Banach space, I'm sorry. So here we'll need the definition. We say that a linear bounded operator admits is representable. We say so is representable if there exists a vector function which plays the role of the kernel, such that for every f from L1 space, this equality holds. And here it is important to emphasize that now we are talking about Bochner integral here. Also, I put one more definition here. I will need it at the very end of my talk, but it is a good place to define it here. So a Banach space is said to have the Radon-Nikodym property if for every finite measure space, each bounded linear operator is representable. So, after that, a strong Danforth-Pettis representation theorem was obtained, which is dealing with weakly compact linear operators and acting between L1 Lebesgue spaces into arbitrary Banach space, which and the range here is separable, so it is representable. The representation equality you can see here on the slide. It was obtained in 1940s, and it is interesting to emphasize that it turned out that the condition of separability of the range space is not crucial. So at the same year, in 1940, Phillips proved the same result, but raising the separability condition. So you can see it here on the slide. The representation is the same, but as you see, the weakly compact linear operators are representable, presented as integral operators, but there is no need to take in the range the condition of separability. So this is the literature. As you understand, we started to speak about linear bounded operators, and here this result is obtained for weakly compact linear operators. Of course, we want to extend the class of operators with which we are working. We need bounded linear operators, but as far as I know, mathematics, nothing can be extended without paying some price for that. And here the price is that we'll have to extend also the space of kernels. This guy gonna be extended also. So let me introduce the class of kernels which will be used here. Okay, we consider vector functions f and j acting into the first conjugate to the Banach space X, or we can also say the first dual to X. And f is said to be weakly measurable if the scalar function, this guy, if this guy is measurable. Also, f is said to be weakly bounded if if it is bounded in norm, which means that the weak norm, which is defined like this infimum, is less than infinity, is bounded. Yeah. So we say that two functions are equivalent as usual when the difference by weak norm is equal to 0. We will need these two notions to define this. L calligraphic means the space of all weakly measurable and weakly bounded functions from omega to x prime. And by L straight, not calligraphic, I define the corresponding space of classes of equivalence of such functions. So, and now we arrive to the weak version of Danforth-Pettis theorem, which is dealing, I wanted to say, with linear bounded operators. And according to this theorem, we can see that the correspondence between linear operators and kernels is given by the representation formula, which is written here on the slide by colored by red. And here we see that in this case the integral is not a Bochner integral, it's ordinary Lebesgue integral. Also, this representation is often called weak representation. So, and the further development of this theory was concerning the following question. And what if our linear operator, linear bounded operator, will work not from Lebesgue space, but from Bochner L1 space? This was interesting, and it was concerning not only the space of where from the values are taken, but also the target space, the range space, gonna be the space of weakly measurable operator functions. And again, we have, if we are considering such class of linear operators, again, the class of kernels gonna be extended. Again, it is analogously introduced, but we have to introduce it anyway. So an operator function K, which acts like this, is called weakly measurable according to x and y if the real valued function here, by the way, I didn't say, but I think that it is very familiar to everyone that these brackets, they mean the bilinear duality form. So operator function K is said to be weakly measurable according x and y if this guy is measurable for all x and y. Also, it is called weakly bounded if this this set is order bounded in L infinity. Also, analogously, we use the notations. This guy is used to the space of all weakly measurable, weakly bounded operators, and the norm is introduced by this formula. So, and finally, we reach to the general representation result for linear operators. It was obtained in 2011 by Mugnala and Nitka, according to which what we have. We have, again, the correspondence between the space of all linear bounded operators acting from L1, Bochner L1 space to here, and the class of kernels acting here. Yeah, and the correspondence is given by this formula. Here again we see that we speak about not Bochner integral but ordinary Lebesgue integral. This formula is, as I told before, is a weak representation, weak integral, we can say also. But it is the most general case in this direction. And as I promised to you, we are working, and I'm going to obtain the generalization, or not generalization, but the analog of this theorem for polynomials, homogeneous orthogonally additive polynomials. But of course, I need to introduce this class of nonlinear operators. I'll try to do it very fast. We call a mapping between two vector spaces x and y to be an homogeneous polynomial, or polynomial of degree n, also they say, if for some multilinear operator, which means as usual that it is linear in each variable, acting from x Cartesian products x and times 2y, this representation holds. Phi in this representation is called generating, and there is exactly one symmetric multilinear operator generating P, generating our polynomial. Next, we'll need to talk about some classes of polynomials which we are working with, but also one more definition. We already used ideal function spaces at the beginning of my talk, but the maybe definition is needed, and I don't know. Anyway, I left it on the slide. So we call linear space, subspace of L0 space, order ideal or ideal space if and only if this condition is fulfilled. Yeah, this one. So ideal Banach space is an ideal space which is Banach space with a condition of monotonicity. The condition of monotonicity is also written on the slide. And finally, polynomial is said to be orthogonally additive if the additivity is fulfilled. Here, if the additivity is fulfilled for any, okay, as far as I'm working in the class of in the class of spaces which are said to be vector lattices, we call two functions for which orthogonal additivity is fulfilled disjoint. But in the terms in which I'm presenting my talk, we can say that two disjoint functions are disjoint. This one is fulfilled. So also polynomial, homogeneous polynomial is said to be norm bounded if it is bounded by norm, and we use the notation where to note the space of all orthogonally additive and homogeneous norm-bounded polynomials on X. It's also interesting to emphasize that in the case when n is equal to 1, we come to the space of linear bounded operators. So here will be, I have only 5 minutes, yeah? Then I will skip several very unfortunately, I have to skip several crucial definitions, but maybe they are not very important to understand the main result which was obtained. I will just say that there is very crucial notion of which is called the power of a vector lattice. Also, it is called in other literature convexification. This is needed because I think that intuitively you do understand why we need the power, because we speak about polynomial. Anyway, you will need to raise into power, and I will leave this mystery in a mystery, okay? So I'll skip it. Also, we need the notion of P-convexity of a Banach lattice. It is also a very crucial notion, but I don't even say why it is crucial. So, and now I can present the main result, which is a counterpart of Mugnola-Nitka theorem for homogeneous polynomials. What we have? Okay, we say that every n-homogeneous, norm-bounded, orthogonally additive polynomial acting from Bochner Ln space into here to be faster. For every such a polynomial, there exists a weakly measurable mapping like this, such that the integral representation is holds. This equality gives us the isometric isomorphism between two spaces, between the spaces of polynomials now and the kernels. And the only difference which is visual, which is easy to be seen, is the fact that, I don't know, can you see it or not, but here is the power, n power, okay? In the case when Mugnula and Nitka were investigating linear bounded operators, it was the same, but without power. And as I told, without degree n, I mean. And as I told, I think that it is expected that the power should appear somewhere here. So this guy is also said, this integral is also said to be weak integral, weak representation. And of course, everybody wants to have, how to say, maybe it's not correct to say, but explicit equality. I mean, when here we have not the bilinear duality form, but when we can write pk is equal to. So to do this, it is necessary to introduce Bochner integral. It is the definition is given here. And if y prime has the Radon-Nikodym property, then it is possible to write the previous equality in this form, in strong form. So this, as I told, or maybe I didn't say it, this is very fresh result. I'm going to prove it as appropriate. I mean, I know the scheme of the proof, and I am more than sure that it is true, but I have to do it, and I hope it will be a new paper, and I don't know how to call it, Danforth-Pettis type theorem for homogeneous operators, or a Danforth-Pettis type, because I don't know which one is more serious. So thank you for attention. Maybe questions.